Hello, and welcome back to the Sleep Lab. Tonight's title carries a little drama, and it's worth being honest about that before we drift any further together. Black holes really do hide something genuinely strange at their center, a place where our best understanding of physics quietly, honestly breaks down and simply stops offering reliable answers. That's not the same as something malevolent waiting in the dark. It's something considerably gentler and more interesting, the edge of human knowledge itself, a place where even the universe's most brilliant physicists have to admit, calmly and without embarrassment, that a genuine mystery still remains. Tonight we're going to walk slowly through 13 genuine, evidence-based facts about black holes, what they actually are, what happens near and inside them according to the best physics we currently have, and where that physics honestly, humbly runs out. None of it should keep you awake. If anything, we hope it does the opposite, since there's a particular kind of calm available in facing a mystery clearly, rather than through the distorted, frightening shorthand black holes so often get reduced to in casual conversation. If this kind of journey is worth your time, a like, a subscribe, or a thought left below helps this small lab keep its lights on for other sleepy minds finding their way here. But for now, there is nothing you need to do except settle in, let your body grow heavy, and let the quiet, honest strangeness of black holes drift gently over you instead. Let's begin. The name itself, so casually familiar by now that almost nobody pauses to question it, actually misleads in two separate, genuinely important ways. A black hole isn't a hole, an absence or gap in space through which something might fall and disappear into some separate void beyond. It's the exact opposite, an extraordinarily dense concentration of mass, packed into an extraordinarily small volume, so much matter compressed into so little space that its gravitational pull becomes strong enough, within a certain boundary, to prevent even light itself from escaping. Nor is it empty, in the sense the word hole tends to suggest. Whatever matter originally formed the black hole, typically the collapsed core of a massive, dying star, remains genuinely, physically present within it, simply compressed to a degree far beyond anything achievable anywhere else in the observable universe. The black portion of the name is considerably more accurate, describing the simple, direct consequence of light being unable to escape the object's gravity once it crosses a specific boundary called the event horizon, meaning a black hole doesn't reflect or emit visible light the way an ordinary star does, appearing instead as a genuinely dark, light-absorbing region against the backdrop of space. Physicist John Wheeler is generally credited with popularizing the term black hole itself in the late 1960s, replacing a variety of more technical, less evocative earlier names that had circulated among physicists studying these objects throughout the preceding decades, a naming choice that, while genuinely useful for capturing public imagination and making the concept memorable, has also, in its own quiet way, contributed to some of the persistent, dramatic misconceptions we're going to spend tonight's episode gently working through, starting with the very shape and substance the name itself so casually implies. Interestingly, Wheeler himself was not the very first person to use the term, since it had appeared informally in earlier scientific correspondence and a handful of prior publications, but his repeated, deliberate use of the phrase during public lectures and widely read scientific writing throughout the late 1960s is generally credited with the term's rapid, lasting adoption across both the scientific community and popular culture alike. Before this naming settled into common use, physicists studying these objects had previously used a range of considerably more technical, less immediately evocative terms, including collapsed star and frozen star, the latter a reference to the very time dilation effect we'll explore in greater depth later tonight, in which an object falling toward such a collapsed star appears, from a distant observer's perspective, to slow and effectively freeze as it approaches the boundary now known as the event horizon, a naming history that offers a small, genuinely interesting window into how scientific language itself gradually evolves and settles, often shaped as much by memorable phrasing and public communication as by any single decisive technical consideration alone. Surrounding every black hole is a theoretical boundary called the event horizon, the specific distance from the black hole's center at which its gravitational pull becomes strong enough that escape, even for light itself traveling at the fastest speed the universe permits, becomes genuinely, mathematically impossible. It's worth being genuinely clear about what this boundary actually is, and isn't, since popular depictions sometimes suggest something closer to a physical surface or membrane, when in reality the event horizon represents a purely mathematical, geometric boundary within space itself, with nothing physically marking its location that a traveling spacecraft or a stray beam of light would actually feel or detect while crossing it. A hypothetical observer falling directly toward a sufficiently large black hole would, according to the physics involved, cross this boundary without experiencing any sudden, dramatic physical sensation at the exact moment of crossing, since the event horizon's significance lies entirely in what becomes possible or impossible afterward, rather than in any physical barrier present at the boundary itself. The size of this boundary, called the Schwarzschild radius after physicist Karl Schwarzschild, who first calculated it mathematically in 1916 just months after Einstein published his general theory of relativity, scales directly and predictably with a black hole's total mass, meaning a black hole containing the mass of our own sun would carry an event horizon roughly 2 miles across, while a considerably more massive black hole, including the supermassive varieties we'll explore later tonight, can carry an event horizon spanning distances comparable to an entire solar system. This mathematical relationship between mass and event horizon size has allowed astronomers to indirectly calculate the mass of numerous black holes throughout the universe, entirely without ever needing to directly observe the black hole itself, simply by carefully measuring the size and behavior of its event horizon's gravitational influence on nearby matter and light. Karl Schwarzschild's own personal story adds a genuinely poignant historical dimension to this discovery worth mentioning, since he derived this now famous solution to Einstein's equations while serving as a soldier on the German front during the First World War, calculating the mathematics from within a military camp and sending his completed work back to Einstein by mail, remarkably managing to solve Einstein's newly published, notoriously difficult equations in their full, exact form well. Before Einstein or most other physicists of the era had expected anyone to manage such a feat, Schwarzschild died only a few months later from a rare autoimmune disease contracted during his military service, meaning he never lived to see his elegant mathematical solution eventually recognized as describing one of the universe's strangest and most genuinely important classes of object, a quietly moving historical footnote behind a calculation that continues, more than a century later, to underpin nearly every serious scientific discussion of black holes conducted anywhere in the world today. At the theoretical center of every black hole, general relativity's equations predict something called a singularity, a point at which the mathematics describing the black hole's structure produces genuinely infinite density and infinite spacetime curvature, values that, taken entirely literally, don't actually make coherent physical sense according to how physicists generally understand the rest of the universe to behave. This isn't a small, minor gap in scientific understanding physicists expect to quietly patch up with slightly more careful calculation. It represents a genuine, honest breakdown in the mathematical framework itself, a point where general relativity, otherwise remarkably successful at describing gravity across an enormous range of situations throughout the cosmos, simply stops producing meaningful, physically sensible predictions. Physicists studying this problem generally believe the true resolution likely requires a genuine theory of quantum gravity, a still undiscovered framework capable of successfully combining general relativity's description of gravity in large-scale spacetime with quantum mechanics' description of how matter and energy actually behave at the smallest possible scales, two extraordinarily successful theories that, despite each working brilliantly within their own separate domains, have so far stubbornly resisted every serious attempt to combine them into one unified, complete description of reality. Candidate approaches toward this unified theory, including string theory and loop quantum gravity, offer several genuinely different, actively researched predictions regarding what might actually replace the mathematically troublesome singularity once a complete quantum gravity theory is finally developed, ranging from an extremely small but ultimately finite region of extraordinarily dense matter, to more exotic proposed structures entirely absent from general relativity's simpler picture. Though none of these candidate theories has yet achieved the kind of experimental confirmation that would allow physicists to speak with genuine confidence about which, if any, correctly describes what actually, physically happens at a black hole's true center. There is a genuinely important, often overlooked mathematical result worth mentioning here as well, called the singularity theorems, developed jointly by Stephen Hawking and physicist Roger Penrose throughout the late 1960s and early 1970s, work later recognized with Penrose's share of the 2020 Nobel Prize in Physics. These theorems demonstrated, through rigorous mathematical proof rather than speculation, that under quite general, physically reasonable conditions, the formation of some kind of singularity is essentially unavoidable once a sufficiently massive object collapses under its own gravity, meaning the troubling mathematical breakdown discussed throughout this section isn't merely an artifact of some unusually extreme, contrived theoretical scenario, but a genuine, mathematically robust prediction. Following naturally from general relativity's own core equations whenever gravitational collapse proceeds far enough, a finding that helped convince the broader physics community that black holes, and the genuine puzzle sitting at their center, represented a serious, unavoidable feature of the theory requiring genuine resolution, rather than a curious edge case safely ignored. Should an object, or in a purely hypothetical, non-recommended thought experiment, a person, fall directly toward a sufficiently small black hole, the differing gravitational pull experienced between the near and far ends of their body would grow so extreme, over such a short additional distance, that the resulting stretching force would eventually pull them into an increasingly long, increasingly thin strand, a genuinely real, mathematically predicted phenomenon physicists have given the deliberately playful name spaghettification. This effect arises directly from a basic feature of gravity called a tidal force, the same general principle responsible for ocean tides here on Earth, where the moon's gravitational pull on the near side of our planet differs slightly from its pull on the far side, creating a gentle stretching effect across Earth's oceans. Near a black hole, particularly a smaller, more compact one, the same tidal effect becomes dramatically, catastrophically more intense over a very short distance, since gravitational strength increases so rapidly the closer one approaches the black hole's center. Interestingly, and genuinely counterintuitively, physicists have found that this stretching effect actually becomes considerably less violent, and occurs considerably closer to the event horizon itself, for larger, more massive black holes, meaning a hypothetical traveler falling into one of the enormous supermassive black holes found at the centers of galaxies, discussed further later tonight, could theoretically cross the event horizon itself without experiencing any dramatic spaghettification at that specific moment, since a more massive black hole's gravity, while ultimately overwhelming, changes considerably more gradually over distance near its correspondingly larger event horizon compared to the much sharper, more sudden gravitational gradient found near a smaller, stellar mass black hole, a genuinely surprising physical detail that inverts the popular intuition that bigger black holes should always be considered more immediately violent or destructive than smaller ones. The same tidal force principle also explains a genuinely important, related phenomenon astronomers have directly observed on several occasions, called a tidal disruption event, in which a star passing too closely to a supermassive black hole gets torn apart by precisely the same stretching force before ever actually crossing the event horizon itself. These events produce a dramatic, distinctive burst of light as the star's shredded stellar material heats up and swirls inward, bright enough that astronomers have successfully detected and studied numerous confirmed tidal disruption events using ordinary telescopes, offering direct, visible, real-world observational confirmation of the same spaghettification physics discussed throughout this section, playing out not as a hypothetical thought experiment involving an imagined human traveler, but as a genuine, periodically observed astronomical event involving entire stars, visible from Earth using instruments considerably less exotic than the Event Horizon Telescope collaboration discussed later tonight. In 1974, physicist Stephen Hawking published research proposing something that initially struck much of the physics community as genuinely surprising, that black holes, despite their reputation as objects from which nothing can escape, actually do slowly lose mass and energy over time through a subtle quantum mechanical process now called Hawking radiation. The underlying explanation involves genuinely strange quantum physics occurring right at the boundary of the event horizon, where quantum field theory predicts that pairs of virtual particles, discussed in greater depth during an earlier Sleep Lab episode covering quantum physics, are constantly, briefly popping into existence throughout all of space, including the region immediately surrounding a black hole's event horizon. Ordinarily, these particle pairs recombine and annihilate one another almost instantly, but occasionally, right at a black hole's boundary, one particle from such a pair can fall inward across the event horizon while its partner escapes outward, and because this outward escaping particle now lacks its usual partner to recombine with, it becomes genuine, real, detectable radiation, effectively carrying a small amount of mass and energy away from the black hole, causing it to very gradually shrink over time. For black holes formed from collapsed stars, this evaporation process proceeds at an almost incomprehensibly slow rate, with physicists calculating that a black hole carrying the mass of our Sun would require a timespan vastly longer than the current age of the entire universe to fully evaporate away, meaning Hawking radiation carries essentially no meaningful, observable consequence for any black hole currently known to exist. Hawking radiation's genuine significance lies instead in its theoretical implications, since it represents one of physics' rare, genuinely successful attempts to apply quantum mechanical principles directly to a problem involving gravity, offering physicists studying the still unresolved quest for a complete theory of quantum gravity a genuinely valuable, carefully tested theoretical foothold, even though the radiation itself remains, even decades after Hawking's original prediction, something no telescope has yet been sensitive enough to actually, directly detect. Some researchers have found a genuinely creative, indirect way to study a close analog of Hawking radiation despite this direct detection challenge, using carefully engineered laboratory systems here on Earth called analog black holes, constructed using flowing fluids or specially structured light-slowing materials arranged specifically to mimic the mathematical structure of an event horizon without involving any actual gravity or genuine black hole at all. In 2019, physicist Jeff Steinhauer and colleagues reported observing a genuine analog of Hawking radiation within one such laboratory system, built using an ultracold, carefully controlled fluid arrangement designed to replicate the same underlying mathematics Hawking had originally applied to genuine gravitational event horizons, offering physicists a genuinely valuable, if indirect, experimental window into testing at least some of the theoretical predictions surrounding this famous, still undetected radiation, even while a genuine, direct detection from an actual astrophysical black hole remains, for now, safely beyond current technological reach. For decades, black holes remained purely theoretical objects, predicted with genuine mathematical confidence by Einstein's equations and indirectly confirmed through their gravitational effects on nearby visible matter, but never actually, directly photographed or observed in any genuinely visual sense. That changed in April 2019, when an international collaboration of researchers called the Event Horizon Telescope Project released the first-ever direct image of a black hole's shadow, capturing the supermassive black hole at the center of a galaxy called M87, located roughly 55 million light-years from Earth. The image itself, showing a dark, roughly circular region surrounded by a glowing ring of superheated gas and radiation, was achieved through a genuinely remarkable feat of coordinated global engineering, linking together radio telescopes positioned at observatories scattered across the entire planet, from Hawaii to Antarctica, effectively creating a single, virtual telescope roughly the size of the entire Earth, since capturing sufficient detail to resolve something as small and distant as a black hole's shadow required a level of angular resolution no single existing telescope could ever hope to achieve alone. The resulting image doesn't show the black hole itself directly, since a true black hole, by definition, emits no light of its own, but rather shows its shadow, the dark silhouette cast against the bright, glowing ring of superheated matter swirling just outside the event horizon, a ring shaped and distorted by the black hole's own extreme gravitational lensing effect, precisely matching the specific visual signature Einstein's equations had predicted decades earlier. In 2022, the same collaboration released a second historic image, this time capturing the supermassive black hole at the very center of our own Milky Way galaxy, called Sagittarius A, offering humanity its first direct visual confirmation of the enormous, previously only indirectly detected object anchoring the gravitational center of our own galactic home. The engineering challenge behind capturing these historic images deserves genuine appreciation in its own right, since the Event Horizon Telescope collaboration required an almost unimaginable degree of precise, synchronized timing across every participating observatory, achieved using extraordinarily accurate atomic clocks at each individual telescope site, allowing researchers to later combine the separately recorded data from telescopes thousands of miles apart with the kind of precision needed to reconstruct a single, coherent image, a technique called very long baseline interferometry. The resulting datasets proved so enormous, several petabytes collected across the entire global network, that transporting the physical hard drives containing the raw data via aircraft actually proved faster and more reliable than attempting to transmit such staggering quantities of information over any available internet connection, meaning one of the most technologically sophisticated astronomical achievements in modern history depended, in its final practical step, on ordinary commercial flights carrying literal boxes of hard drives to a central processing facility, a genuinely charming detail illustrating how even cutting-edge science sometimes still relies on refreshingly simple, practical solutions. Beyond the more commonly discussed stellar mass black holes formed from individual collapsed stars, astronomers have found compelling evidence that nearly every sufficiently large galaxy throughout the observable universe harbors an enormous supermassive black hole at its very center, with masses ranging from several 100,000 to many billions of times the mass of our own Sun. Our own Milky Way galaxy's central supermassive black hole, Sagittarius A, directly imaged in 2022 as discussed a moment ago, carries a mass roughly 4 million times that of our Sun, and astronomers first confirmed its existence not through any direct observation of the black hole itself, but by carefully, patiently tracking the orbital motion of several nearby stars over more than 2 decades, finding that these stars followed orbital paths that could only be explained by the presence of an Extraordinarily massive, invisible object at the orbit's shared central focus, a discovery recognized with the 2020 Nobel Prize in Physics, awarded jointly to Reinhard Genzel and Andrea Ghez for this painstaking, decades-long observational achievement. The precise mechanism by which these supermassive black holes originally formed remains an actively researched, genuinely open question in astrophysics, with several competing theoretical models proposing different possible formation pathways, including the gradual growth of an initially much smaller black hole through the steady accumulation of surrounding matter and repeated mergers with other black holes over billions of years, or alternatively, the direct, rapid collapse of an extraordinarily massive cloud of primordial gas relatively early in the universe's history, bypassing the intermediate stellar formation stage entirely. Astronomers studying the relationship between a galaxy and its central supermassive black hole have also found genuinely compelling evidence that the two appear to grow and evolve together in a closely coordinated, mutually influential way, with a galaxy's overall size and structure correlating measurably with its central black hole's mass, a connection researchers continue actively working to fully understand and explain. This close, coordinated relationship between a galaxy and its central supermassive black hole is sometimes referred to by researchers as the M-sigma relation, a mathematical correlation discovered independently by two separate research teams in the year 2000, connecting a supermassive black hole's mass directly to the velocity at which stars orbit within the galaxy's central bulge, a correlation so consistent across the many galaxies studied that it strongly suggests some genuine, ongoing physical feedback process links the growth of a galaxy's central black hole to the broader development of the entire galaxy surrounding it, rather than the two evolving as separate,